Screen I'm sharing. Share the screen.
I heard it.
Yeah, seems to work.
I am wait. Yes, okay, and type it. All right, perfect.
You've got the entire slide.
Say again?
You've got the entire slide or not?
No,
Yeah?
I see the editor view. If you present.
Yeah, if I put the present, that's fine. Exist?
Perfect. Yeah, I can see it. So let me see 1 second. The streaming is now on. Let me actually just. All right. So then let me start the recording, and then it'll just be a really quick intro. So I'll give you more time. I think it's about time now. 1 minute. Wait, is your last name Salles or Salles?
Oh, Sal.
Sal. That makes sense.
No pronunciation of the S at the end.
Yeah. All right. So, hi everybody. I'd love to introduce Tristan Salles from University of Sydney, who I guess you track the entire history of Earth from the little we can see, from looking deep underground and whatnot. But you're the ultimate historian. Yeah, welcome.
Sure. Cool. Thank you. Are you seeing? Yeah. Okay. Cool. I can start. So first, thank you for giving me the opportunity to present today. And yeah. So as you were mentioning, I'm going to basically talk about landscape dynamics and looking at it over geological time, so several hundreds of millions of years. And what what is different from what people have been doing in the past is basically looking at it on a global scale perspective. So looking at the entire planet evolution. So this work, I'm presenting it on behalf also of many of my collaborators in different places. So Laurent Husson and Manon Lorsory, who are based in University Grenoble-Alpes. And I've got also several colleagues from the University of Sydney, Sabine Zejovic, Claire Mallard, and Beatrice Boggiani. And also some colleagues from the École Normale Supérieure of Paris, Nicolas Coltis, and University of Lyon, Maëlys Arnaud. So before starting to dive into, I guess, the paleo evolution of Earth, I'm going to quickly give you an idea of the topic. And basically, I like this concept of looking at the Earth's surface as the living screen of our planet. And the Earth's surface is actually, so what we would call the Earth's surface or Earth's topography is basically the change in elevation over the surface of our planet. And basically, it's a combination of different forces that act on this surface. So the first one is tectonic, or also which integrates different forms from fault activity, but on the kind of long time scales that we are looking at, it's mostly driven by plate tectonics, and which basically is going to move the surface up and down and creating a mountain range, which is this kind of much I would say critical evolution of this tectonic forcing. So you've got an example here of the Himalayas mountain range, which formed by basically about like 50 to 40 million years ago, as a result of the collision between two tectonic plates, the Indian plate and the Eurasian plate. And on the other side, you've got other processes or other forces that are going to drive this change in landform, and it's basically the surface processes, which are usually related to gravity, but also to different forcing induced by climate. So it could be a wind, wave, or ice, and these combined forces are going to basically change the way the elevation is going to evolve by basically transporting or eroding sediments, let's say from mountains to alluvial plains, and depositing them in the marine environment. An example of the most distal terrestrial kind of environment that you will find will be like this big deltas that form at the mouth of river mouth, at the mouth of main rivers. And you've got an example here with the Lena Delta in Russia. This is also a place, for example, this delta where you will basically have a huge explosion of life. And we know that, by let's say 500 million years ago, at the beginning of the Phanerozoic, life basically emerged from the ocean and migrated to the continents. And this is likely places like this, which were the most the best place to have this kind of migration from biodiversity from the ocean to the land. When we think us, and not just the general public, but also many scientists, when we look at the landscape, we often assume that they are relatively steady and stable. For example, we will think that a mountain has always been there, and there is not that much movement. Of course, there is some processes that we can see and feel, for example, like landslides or floods. But overall, people have always thought that the changes that are happening are quite minimal. In reality, landscape are transient, and they will respond. I will say quickly. For a human, it might not seem that quick, but they change overall. If we look at periods of thousands to millions of years, they are changing drastically. So what is the reason for looking at Earth's evolution over millions of years? Basically, what we know is that the Earth's landscape is a record of what happened in the past, and also can give us some clue about how this surface is going to change in the future. And there is many reasons why we should look at it, but here I'm just providing three, which I think are really important reasons. First one is that we know that Earth surface processes are basically playing a huge role in regulating our climate by basically pumping the CO2 in the atmosphere through different processes, which are physical, mainly physical and chemical weathering, where the CO2, which is in the atmosphere, is going to be dissolved and transported by rivers into the ocean. And so this is going to play a huge role in basically regulating the temperature of the Earth. Another reason is that we still have some, we still don't really understand why there is some places which have a huge or high biodiversity more than others, and we can see that in different time during the past evolution of the Earth. And all this basically Earth surface is actually driving different environments that can lead to change and also to evolution of life on Earth. I'm not going to touch upon this, how it can be used in the future, but basically by trying to evaluate how this Earth surface has changed in the past, we might be able to have some ideas about the repercussion of the way we have changed our landscape and also changed the climate. So now let's and oh yeah, maybe I can talk about this. I couldn't resist to put this nice diagram from Van den Bolt here from 1841, which shows basically a description of how the surface and the related rock behind it, so stratigraphic layers behind it, is corresponding to some specific type of species that we see. And so these questions that I just put at the top here, basically they can be traced back to what was what Darwin or even Wallace was thinking, several, more than 100 years ago. So now let's dive into, what when we talk about paleo-elevation or paleogeography of the Earth, what are we talking about, and basically how we design them. So most of the time, these paleogeographies, they are actually designed based on three different parameters, three different things. So first, what people have been doing is trying to do some inference from present-day processes. So, for example, you will look, I don't know, at the Mississippi rivers and delta, and you will get a sense of how big or how much flux in terms of sediment and water you need to create a specific type of delta. You will look at a mountain range to also evaluate the amount of erosion that you might expect. So people looking at present day to try to describe what they see in the sedimentary archive. Another big theme is basically trying to reconstruct the evolution of plate tectonics over millions of years. And to do that, what we have is basically a lot of geological dataset, but this dataset is often limited in terms of spatial and temporal resolution. So there is likely no continuous geological data. So basically we have to make some inference from this data. And here you've got two examples. I will maybe start with the one on the right here, where we've got a paleogeography which has been reconstructed so that the underlying color map here, which basically shows how this map has been reconstructed. So it's for a specific period at 70 million years ago, which basically has been designed based on looking at drilling sites and looking at paleobiology database. Another example on the movie here on the left is again designed based on paleobiology database. And as you can see, this paleogeographies is nothing like what you would see if you go on Google Earth today and look at the Earth surface in terms of resolution and in terms of landforms or variety of landforms that you will find in these paleogeographies. They are pretty limited. So, for example, on the movie here, you can see we've got pretty much two types or three types of landform. We've got mountain range, which are these orange polygons. We've got the landmass, which is this yellow part. And also described here, we've got the shelf around the continent, so the shallow marine area. So this seems pretty simple as it is in terms of representation of the Earth, but this kind of paleogeography has been used and basically underpin many aspects of how we have been describing the evolution of our planet over millions of years. For example, and they have been used in many, in pretty much all paleoclimate models as initial inputs for running these atmospheric and oceanic models. They have been used extensively to try to estimate and predict where we could find some natural resources, and also they are they are used as input for understanding the origin and evolution of life, for example, in mechanistic movement. So what we thought and what we did in our study basically was to actually look at this paleogeography and trying to see if from this reconstruction, which are mainly qualitative, basically, is there a way to define a framework or a kind of methodological approach that could allow us to have a better quantification of this reconstruction. So to do so, what we did is basically trying to combine the different informations that we had. Here, the idea is that we've got some reconstruction of paleoclimate. We've got some reconstruction in the past of the tectonic evolution. So it can be plate tectonic, or it can be tectonic related to the movement of the core of the Earth and the mantle of the Earth. And basically combining that with paleogeography reconstruction and evaluating the amount of erosion and deposition, and trying to have a better representation of the physiography or the geomorphology of the Earth. So to do that, we basically design a tool which basically is a pretty simple tools in terms of the equations that we use. This is an equation which is used in many other landscape evolution model, which will describe the change in elevation over time using the uplift, so the up and down of the surface, and integrating two types of processes. So the first one, maybe we can start with the hill-slope processes, which is like a gravity-driven processes, and which basically is a diffusion law, and a second process which is related to rivers. So there is other processes, obviously, that are going to impact the surface of the Earth, such as a landslide, for example. But we choose to use rivers here because they are considered, and like again, this is an analogy maybe with a human body. Is basically rivers, they are seen as a circulatory system of the Earth's surface, which is transporting the sediments from mountains to the ocean, and so to simulate these rivers, we use a simple law which is called the stream power law, which basically scale the amount of incision to the slope and to the local slope, and the amount of water that is flowing through a specific node. And so we designed a tool.
Question: what timescales does this cover? This seems like a erosion of Himalayas down to nothing kind of a process. Is that it, or is this applicable to like whole continents moving around and tracking that process?
Oh, so you can track. Basically, you can track this kind of equation here has been used usually at local scale. So you can really look at a specific catchment and look at the evolution of the river, of a specific river in that catchment by using a time step, which usually these models are used for looking at from decadal to centennial and millennial timescale.
Okay, so these are still like civilizational timescales. We're not talking about Himalayas eroding. That would be
no. Yeah. And basically, what was the main, the most complicated thing in designing this tool was to find strategy to implement a parallel approach of the tool. So the code that we run here it can be run on supercomputer over like hundreds of CPUs. And that's basically the main difference with what others model have been doing. And the other thing is related to the fact that we are using an implicit method which allows us to extend the time step when we solve the equation.
Okay, so then what's the temporal resolution doesn't tell you because you're implicit, but what's the spatial resolution?
So the spatial resolution. So in the model that I'm going to present, so here we are looking at the entire planet, and we have a resolution of 5 kilometers, around 0.05 degrees. So 5 kilometers at the equator, basically.
Perfect. Thank you. Oh, and what's the time scale? Like we're talking about like 1,000.
So the time scales here for this specific model, we run a time scale. don't remember exactly, but maybe it's like every 1,000 years or every 5,000 years. That's the time steps that we use.
Oh, okay, that's one time step. And then the total run? What's the total run?
Oh, the total runtime? You mean of
of the simulated model?
As a simulated model, so I will present two models. One is 100 million years, and the other one is 500 million years.
Got it. Thank you.
So basically, the way it works is we've got a set of inputs, which are elevation, climate, and tectonic. We put that in our surface process model. And what we got out of that is a description of the landscape dynamics, but also many other things, such as the flux of water and sediments. Also, we can look at what is called the sediment routing system. So basically, we can track specific sediments from a specific region and where they will end up. And we are able also to reconstruct the evolution of sedimentary basins, which is basically critical if you want to compare your data, your model output with data. And so from these outputs, what we can do is we can then, compare them with empirical data sets that exist, and look at how the model basically is able to recreate or match with some data. So that's a first way of looking at this. The second way is basically we've got this set of reconstruction, so a specific paleogeography reconstruction, a specific climatic reconstruction, a specific tectonic reconstruction. And what we can do is we can combine them together and see what kind of output we get out of them. And by that way, trying to quantify how this set of reconstruction are able to reproduce or represent what we see in nature.
So then it looks like you have tectonics as an input. So you're assuming some other model is giving you the uplift of plates and whatnot. That's independent.
Exactly. So the idea is the inputs here. Okay, they are what people reconstructions that exist that are based, specific knowledge of the Earth system. And what we can do here is basically test how a specific reconstruction is able to reproduce some data that we've got. And so basically by that way, trying to figure out a more quantitative way of assessing this reconstruction.
Got it. So it's another form of validation. But then how do you make sure that your climate really is going to be affected by the phenomena you're showing? If there's a mountain or if it has or has not eroded away, that changes the amount of precipitation. So how do you ensure this consistency?
So basically, this model, the climate models, usually they are the paleoclimate models that are available. When you look at several hundreds of millions of years, they are like 2 degrees to 3 degrees resolution. Okay, so the idea here is that we start with what is called the elevation. Here is the paleogeography. So this is the coarse kind of shape of the Earth's surface, which usually has been used as input for the climate model. So by that way, what we have is something which should be relatively consistent in terms of climate with the paleogeography. Yeah. Of course, what we do is basically we've got something which is going to be at much higher resolution in terms of elevation. And the next step that we haven't started will be basically to potentially do some downscaling to improve on the climatic prediction.
I see. So based on your predictions of what the shape of the surface becomes, you can go back to the climate model and refine it.
Exactly. We can basically try to refine. So there is two aspects of it. There is one aspect which is basically looking at what we've got and trying to quantify how this reconstruction works. And there is another aspect which is from a better representation of the elevation, can we improve some of this reconstruction by using downscaling, but also by potentially changing the paleo elevation to adjust to adjust and to better match with the empirical data set.
Right, makes sense. You're fine tuning the input to ensure consistency, because once you have a cycle, you have the chance to look at consistency.
Exactly.
Okay, got it. Thank you.
And so here, for example, you've got two snapshots at different times from our model. So if you remember one of the first slides where we had this representation of the paleogeography with polygons, you can see we've got a much higher representation, a much better representation of the landforms. So what you've got underlying is elevation, and on top, on top here we've got the river network, the drainage system, and this part there, they are like big lakes, or potentially it's like floodplains, or it can be, depending of the climate, it can become like dry lands. Okay, and so we can look at this evolution over time, and another snapshot showing pretty much the same thing, except that you've got here on the right, you've got the amount of erosion and deposition. So in purple you've got the erosion, and in orange you've got some deposition. So this could be used, for example, there is methods to date the exhumation of a mountain, and you can use the denudation rates that is produced by the model and compare that with dating methods. And similarly, you can look at the sediment record in different places, and if you've got some wells or some seismic, you will be able to basically compare the data with the output with some of this data set. So what we presented in the paper was basically looking at the evolution over the past 100 million years by combining one set of reconstruction which is called the paleomap reconstruction from Scotties, which basically look at the evolution of the plate tectonic and provide with it a paleogeography, and using a paleoclimate model, which has been run with the paleomap dataset to ensure that consistency between the two. And what we did was basically running our models. So one thing to note that I didn't really mention before is like the paleogeography themselves, they are not continuous. Okay, usually you will have data every approximately every 5 million years. At 5 million years interval, you will have a kind of average representation of the paleo elevation. And so basically what we do is we run the model for, let's say, for 5 million years interval. We do that back and forth to ensure that our model reproduces the average shape of the paleogeography, obviously with more resolution and information in terms of landscape definition than what you've got in the paleomap, in the paleogeography. So to give you an example, an idea, this is like the Scottish paleomap here that we had just interpolated from its resolution to 0.1 degrees. And here is the reconstructed, or the paleophysiography that is simulated from our model. So there is many things, there is many features that are created. So these features, they are consistent with the paleoclimate reconstruction. Okay, so it's based on the amount of rain that you've got in the different places that basically create this kind of landforms that you see on the in a paleoclimate model. So we will run the model by imposing the paleoclimate, the tectonic, and reaching what we call a dynamic equilibrium, which is basically when the erosion is compensated by the amount of uplift that you've got. So for that, we run the model for 1 million. We run it until we reach this dynamic equilibrium. Usually it will happen in less than a million years. And so from that, what we say is basically the landforms that is created here is a representation of the time intervals that we are looking at. And basically the idea is that if you compare the top and bottom elevation, there is much more information in the one in the bottom, but basically they have the same kind of elevation range distribution. So here you've got a hypsometric curve, which is basically an histogram showing the percentage of area which has a specific elevation, and you've got in purple the initial paleogeography, and in black the simulated one. So basically we've got relatively the same distribution, except that the model has a bit more information on our case.
So let me understand this. It seems like the challenge you're facing is actually common for agent-based modeling too. The resolution of your simulated elements is much finer than the system you're modeling. And the data you have there is rather sparse, and there's no, because you never have initial conditions accurate enough, you will never reproduce the exact landscape that happened that time anyhow. So all you can do is say is it roughly the same number of mountains as valleys as in the real data set? And I don't care where they are. So it's a windowed distance kind of. So yeah, you have two vectors and you're doing like a windowed difference between them as opposed to like an exact cell by cell difference.
Yeah, exactly. And that the idea is that what we are trying to achieve here is to have a better, I mean, we know it's never going to be what it was,
right.
But what we want is to have a reconstruction which is actually going to have much more complexity and which at the same time consider what the other reconstruction have been doing. And the idea is that then you can like use and test different reconstruction and see how these reconstruction are performing. And to do that.
So then how do you deal with, let's say a river delta, and you say this is definitely going to be a river delta, and the way of describing a river delta, it seems like multiple different shapes will have the same, this metric, that distribution of heights, as a river delta. But river delta is a particular shape of such heights. So is there a way of capturing like spiky mountain, smooth mountain, river delta, plain, that's more refined than this, which my intuition is that multiple different landforms might have the same shape here.
Yeah, so for a delta, it's not that, I mean, if you're lucky and the delta is still preserved, it's not that hard, because you can basically look at the sedimentary archive and see what your model is predicting and compare that with the data that you've got.
Because your data is much more fine-grained in that case.
Then this not more fine-grained than a seismic data, but for example, yes, if you've got only a well, okay, a drilling site somewhere, yeah, after you can extrapolate as much as you want.
Right.
Yeah.
So that's rather, that's rather coarse. But I guess you're saying that you're not going to get much data anyhow, so you never had a chance at inferring watershed or anything of that nature, or delta.
Well, it's difficult.
That makes sense. Okay, thank you.
But just to give you an idea of the outputs, so I talked already about like the drainage river and the lakes. What we've got is we've got also access to, over time, the evolution in terms of erosion and deposition. And we are also recording the stratigraphic layers. So how sediments basically, which is deposited either inland or offshore, are basically the different package, how they are deposited and what their shape is. And these specific stratigraphic layers or sedimentary basins filling basically can be used to do this kind of comparison with present day. So for example, here is a cross-section in South America in different places. So what you see first is that the depending of where you are, you have really different kind of sedimentary feeding architectures that you can compare if you've got some data. So for example, this section 2 here, there is some seismic, and that's what is predicted using the Scottish and Valdez reconstruction. And so you can make some comparison based on time and on sediment accumulation and see how your model is performing. Yeah. So in this case, this is I mean, in our case, we were happy with this kind of one-to-one comparison here, where we see that there is, it seems that the different layers in terms of time and thickness, obviously, they don't really have the same final shape, but overall, the trend seems to be similar, with the amount of accumulation at different periods of time seems to reflect what you see in the seismic. For example, for section 3 here, which is like crossing a mountain range, which is called the Tandilya High, what we see is that the history is not reflecting basically the interpreted tectonic and sedimentary evolution of the region. What we have in our case, we see that basically the apparition of the Tandilya height in the paleogeography that we use is happening maybe too late in the model. And by doing so, we've got a late surrection of this region, which expose some sediment at the top here that we can't really notice in the seismic. So what we think needs to be done in this case is basically go back to the paleogeography and fine-tune this orographic belt, basically to improve on what the model is able to predict. So using this kind of one-to-one comparison, we can find places where it seems overall to work all right, and others where there is some discrepancy between what the data is telling us and what the reconstruction is doing. And this kind of tool basically help us to get a sense of where there is these problems and what kind of thing needs to be changed to improve on these models.
So in this figure, I see you have one example, like section 2, that has predictive versus seismic. Are the other ones showing those comparisons, or because I'm trying to understand where you go wrong? What are the challenges?
So the challenge is basically here we've got some sediments that initially what we've got in this model is that the Salado Basin and Colorado Basin initially they form a huge single basin in our case, and you can see the strategy, the layers there, they are pretty continuous over the two basins. And this is because when we start, because in the paleogeography, there is no mountain in the middle. Okay.
Oh, that late surrection? That's missing for you?
And the late surrection is that basically the surrection, the uplift or the apparition of the mountain appears too late in the model. So these two basins are not actually separated early on. And we can see, and basically this is what and from looking at the seismic data set, we know this is not the case. We know that there were actually different basins. So looking at what the model is predicting and what the data is telling us, basically we've got some ideas about what is missing or what kind of information needs to be added to the paleogeography. So from that to let's say the Scottish paleogeography and get a Tandilya height which is appearing earlier than what it is in the reconstruction.
Okay. So is this something that I guess there's two phenomena here. One is your model is not accurate enough, like the actual equations. The other one is that there's a driving boundary condition, like this thing. You should have had it, I guess it sounds like, earlier in the model, but it was time shifted later. So I guess to what extent do you it sounds like the latter, that your boundary conditions tend to be problematic, is where you're seeing the problem.
Yeah. Yeah.
So then, is this an opportunity? I mean, this makes me think of what does machine learning do? I mean, you can generate various phenomena like an uplift and see which ones happen to improve the accuracy of your model, and says like, oh, that, yeah, as a debugger, that might be something I could explore further.
Yeah,
exactly. Is that viable, or is it too random?
No, I mean, that will be valuable, and there is people doing that, not at global scale, looking at a specific catchment. People are doing this kind of thing. So, you will basically generate different scenarios, test them against the data, and that's how you will basically improve on your understanding of a specific region evolution. Okay.
Okay, makes sense.
And that's things that are done at regional scale or looking at a catchment. When you start to move to global scale, the problems that you have is like if you want to run, for example, if your idea is to run, a model where you will generate different kind of climatic conditions that are going to be feasible, and generate then after your landscape evolution model, it will take a lot of time to run. So in this case, like you need, I mean, I'm sure this is possible, but this is not something that has been done yet.
Makes sense. Thank you.
And another example, and to come back to what you were saying, is basically here we've got looking at the outlet of the Orange River in South Africa. So that's the position of the Orange River based on the plate reconstruction. So here, I mean, up to now we talk about like paleogeography. We talk about the climate and the issues that you might have with the climate, and there is also like problems with plate tectonics reconstruction. You don't have a single plate tectonic reconstruction. You've got different scenarios based on different interpretation. But with the plate tectonic model that we use, that's the position of the Orange River mouth over time, over the 100 million years. And what we can do with the model is extracting the amount of sediment which is carried to this outlet over time. And that corresponds to this orange line here. And you can compare that with estimates of sediment accumulation based again on wells, so drilling sites, and also like seismic that has been done in this region to evaluate the amount of sediments that were carried by the river. So, and this corresponds to this green or teal line here. So again, here what you can do, so you see that there is first overall, and that's many of the things I'm talking about, I'm saying overall, first order, but basically over the first 20 million years, we see that there is a sediment pulse, okay, which is represented by both the simulated model and the measured data. Then after you've got a period where there is not much sediment going on, so potentially induced by climatic changes, so less erosion inland. And you've got a kind of a second pulse, which is a bit higher, I mean, which is higher in the simulated model than it is in the measure one. Knowing that even for the measure one, people are basically arguing about this pulse and how much actually sediment volume was deposited over this last 20 million years. So even when we look at this here and say measured, it's interpreted based on data that you've got today. Okay, so there is no like a definite answer or anything. But what we can do so with this model is basically looking at the denudation rate. So here I'm looking not just at the 100 million years. We run a model for the entire Phanerozoic, so for like 541 million years, and that's the mean denudation rate predicted by the model. Okay. This is here data from, let's say, a present day or from the Neogene so the last, let's say, 5 to 10 million years. So values that are proposed in the literature, they range between 63, 63 being the mean. You've got values that range between 50 and 78 meter per million year. And what you've got here in pink is the estimates from the sedimentary record. So we know that the sedimentary record is going to be incomplete because there is many sediments that were deposited at some stage that have been eroded over time. But basically what the model can help us investigate is how this denudation rate has actually changed over time. So to conclude on this part, what we've got here is a model that is able to extract some information from this reconstruction and try to design. And we basically design a tool that can quantify how these different reconstructions are working. And we believe that it can be used to improve on available paleo-elevation and paleo-climatic reconstruction. And at the moment, the process that we do to make this improvement is mostly like looking at specific places around the world. But obviously, there is a work that can be done to improve on the way we evaluate these models. So on a second part, I will discuss more about this idea of a circulatory system and how rivers are playing a role in the evolution of life. So as I mentioned before, what we can do with this model is looking at different catchments and different rivers and looking over time as how these rivers have evolved and how the catchments have evolved. So here is an example where we got on the left water fluxes and on the right the sediment flux. So usually the places which have the biggest water flux, they often have the biggest sediment flux, but it's not always the case. For example, if you've got places where there is less rain or the catchment are quite small, but they are on really steep slope, like for example on the edges of the Andes, you might be able to have a lot of sediments that are going to be carried out to the ocean, even if your drainage and your rivers are small.
Question. So yeah, you're tracking the deltas, not the intermediate river structure, right?
Oh, no, we are tracking the rivers.
Gotcha, okay.
Yeah. Here I'm just looking at the deltas, okay? But, and what you've got here in the bottom is the circle in the ocean. They are the total net sediments which is going to go inside in the ocean, okay, which are eroded by rivers. And what you've got in red is the sediments which are going to be stored in continents, okay, to creating like big sedimentary basins.
Got it.
And what we can do is we can track that over time, okay? In blue, what you have is the total erosion flow. In purple, the amount that is going out to the ocean. And in orange, the amount that is stored inland. So we see that there is a kind of, if we start in the Cambrian here, it's relatively flat, and we've got a kind of a plateau. And then after, by the Triassic or Jurassic, it starts to go up. And it matches really, pretty well with the timing of different type of mountain range episodes, okay? What we looked at was trying to see if there was any relationship between this sediment flux and the evolution of marine and terrestrial life. So the first thing is we looked at marine animal families. So here we've got the number of marine families over time. So we start with a Cambrian explosion by before 500 million years. Then we've got this great Ordovician biodiversification event. So globe, and you can see after we've got a kind of a plateau, a big drop here during the mass extinction, and then after a rise during the Triassic. So if we superpose our net sediment flux to the ocean, okay, so the one that is basically going to go directly to the ocean, we see that we've got an initial, not an increase that starts during the Cambrian, but just at the end of the Ordovician here. And then after we've got a kind of a plateau, we see a decrease, and then after we've got this increase as well. If we look at simply the linear relationship between the two, we've got a correlation that indicates like a strong linear relationship between the two. What we hypothesis is that basically the capacity for marine life to evolve is related to sediment flux. And actually what rivers are doing is basically bringing nutrients which are key for primary production. And from looking at this general trend, we suggest that basically abiotic controls, which are like physical controls, which our model is basically able to reproduce because it accounts for tectonic, climate, erosion at the surface. So it integrates all these different, or the main aspect of the abiotic controls, is basically as important as macroevolution in the evolution of marine life. And we can do the same this time looking at plants, but for plants what we are able to do is, in addition to looking at sediment flux, is also to look at the evolution of the physiography complexity. As I mentioned before, in our models, we've got like different type of landforms that like canyons or valleys, inside valley in different places. So what we can do is we can use that and define a metric that basically characterize the complexity of the landscape, or we name this metric the physiography diversity, and it encompasses, for example, so here you see the water fluxes. We've got at the bottom here, we can see like we've got all the rivers, and they are going to carry the sediments in them. We are using the slope. We are using the topography position index, which is characterizing the rugosity of the landscape. And so we combine that together to form this physiography diversity index. And then after, what we do is we try to compare both the sediment flux, but this time which is stored inland, and our physiography diversity with the evolution of a plant. So we start, like if we look at the evolution of plant, we start in the Silurian. So it starts a bit later than the evolution of marine life, but we've got initially some early vascular plants, which are like non-rooted plants, basically. And we go to something where we got the gymnosperm, which are a rooted plant, up to, let's say, the Cretaceous, just after the Jurassic, I would say. We start to have the explosion of the angiosperm, so the floral plants. So if on top of that we add this time the amount of sediment, or the area of sediments, the area of continents that are covered by sediments, this is the red line here. And if we combine that with this time also the diversity of the landscape, which is shown at the bottom here, we find again, if we do a kind of a simple linear relationship, we find a correlation of 0.9, again, suggesting a strong relationship between the two. So in this case, what we suggest is that landscape, by creating opportunities for sediments to start to deposit inland, basically formed soil that facilitates the development of plants. And
so in this case, it could the causality be in the other direction? The more plants, the more soil, the more sediment?
The other way around, we say the formation of soil
So before it was marine organisms. Marine organisms are not creating sediment, but plants, which are many of which are on land, can create sediment. So at that point, there's a causality question.
Yeah, so you're right. So there is also the formation of plants is also important for formation of soil. And
exactly.
Yeah, exactly. And so we are not, and there is a lot of, I mean, there is not a lot, but there is some research that has been done suggesting that this is actually the formation of plants that drove the evolution of rivers and landform in. Okay, so I'm not saying that this is fully this is explaining everything, but what we see is that there is a strong relationship between the two. After which one is controlling it's controlling the evolution of the other. From what we do in our models, basically the plants, they have no impact on the evolution of our sediment flux and on the formation of soil. Because we are just tracking sediments in our case. What we can think, what we can hypothesize is basically as you increase the number of plants, specifically rooted plants, you will also increase the amount of soil that is available and increase also the erosion. But this is not considered in the model. One thing that one thing that is important to note also is that here it's not just the sediment that is going to be deposited on the continent, it's also the complexity of the landscape. The fact that we, through time, we start with a landscape that is relatively homogeneous, okay? And over time, this landscape is going to start to become more and more complex as you start to have more mountain ranges, you start to have some valleys that in size, and all this is going to complexify the landscape, making it more prone for specific species to develop in specific environment. So it will help to increase the number of ecological niche or increase the number of environments that you will find on Earth. So to conclude on that, I think the idea is that what we think is that the marine diversity is directly scaled to sediment flux, and sediments in this case which are bring by rivers are also a good proxy for nutrients. And that land plants diversity is in fact going to start when sediments, a large portion of sediments is able to accumulate in the continent. And so what we think overall is that the physiography changes determines the carrying capacity of both ocean and continents. So to conclude, the idea now that we have is to try to combine these different spheres and integrate them together in a better way by combining mantle convection models that are able to produce a change in landform like at broad scale, integrating like general circulation models and surface process model, and looking at that after to inform on biodiversity evolution. And that's it for me.
Yeah, well, thank you. It was fascinating. Thank you very much. I think nobody asked all the questions that I had, but yeah, this is fantastic. Yeah, and when you get a chance, please send me your slides so I can make them available.
Sure, no problem.
Great, thank you. Well, have a great rest of your day.
Yeah, you too. Bye.
Bye.